In a sequence of videos, we will introduce two robot control. The first video is about the basic structure of the robot controller. In the current video, I give you an overview of robot control and introduce you to the structure of robot control, architecture of simple axis controllers and position and velocity controllers. In later videos, we will take a closer look at the parameters for position and velocity controllers, the kinematic controllers, the limits of controller settings, the cascaded kinematic controller, and control using the dynamic model of the robot. First, we will look at the typical structure of a robot controller. Let us first consider a simple axis controller. On the left in blue, we see the robot controller, and on the right in yellow, the robot. A task triggers a pass command that starts the pass planner. In Eros, this triggering authority would be the sequencer. A trajectory planner generates target positions, which are represented here as a stream of geometric location vectors P. These are converted into generalized robot coordinates by the inverse transformation and are represented here as a mathematical vector with the formula symbol Q. The index D means that it is the desired value, also called set point. This flows into the control. The robot has joint sensors with which it determines the current position. This position is also represented in generalized robot coordinates. We usually indicate actual values by not using any index. The controller compares the set point and actual positions, uses them to calculate the positioning forces represented by the mathematical vector Q, and controls the robot's motors accordingly. Normally, this controller structure is realized as software. The control algorithms in the control system must be periodically computed in hard real time, while the robot application sequences are processed sequentially without any specific real-time requirements. Sometimes a velocity measurement system, such as a tachometer, is also used to improve control. In these cases, it is useful for the path planner to calculate the Cartesian velocity in addition to the position set point, which is then converted to velocities in generalized robot coordinates by multiplication with the inverse Jacobian matrix. A cascaded controller is a controller in which there are two nested control loops instead of one. In cascaded control, the generation of set points and actual values is the same as previous shown, but the controller provides a velocity at the output instead of a force. The velocity controller receives this velocity set point and the actual velocity value from a sensor and uses it to calculate the actuating force applied to the robot in generalized robot coordinates. Path planning and position control are again performed in software, while speed control also can be performed analogously by independent electronics. However, these electronics are nowadays usually also implemented with a microprocessor. Let's go a little deeper into these considerations and see how a simple axis control is built. Let's take a closer look at the internal structure of the previously presented position controller. The controller requires the difference between the set point position and the actual position in order to calculate its correction force. We refer to this controller error here as E. But since it is a second-order system, the controller could oscillate undamped, which is why we also need the derivative of this error, which we denote here as E dot. This derivative is identical with the velocity error. If we want to control the velocity, we can use the same control structure and calculate the position error by integrating the velocity error. Control parameters would remain the same, but one would of course have to prevent the position error from running away uncontrolled by integrating a small error into the velocity measurements. If it is possible to measure the speed, then very accurate control is achieved if the corresponding target speed is also determined in the path planner. Let us now take a closer look at the cascaded controller. The speed controller in the inner control loop receives the speed set point from the outer controller. It calculates the control error as the difference between the set point and the measured actual speed value and uses this to determine the actuating force applied to the robot. The superimposed position controller in the outer controller loop compares the set point and actual position and uses this to determine the correction speed that is applied to the speed controller in order to maintain the required position. Unfortunately, with this architecture, the position controller provides a velocity set point that is zero when there is no position error. The robot therefore only moves when there is already a position error. If you set the controller like this, you would have a very large tracking error. This is of course undesirable, which is why in the case of the cascaded controller, a set point speed is added, which corresponds to the position set point and is often determined from it, as shown in this example. This is called an additional speed feed-forward control. With these measures, the cascaded controller behaves exactly the same as the PD controller, has the same step response, the same frequency response, and the same tracking error. Now we address the control parameters. We have seen that we must always consider position and velocity errors in the control of robots. In linear control engineering, the simplest way is to multiply the position and velocity errors individually by a constant and add the results. In position control, we call it a PD controller because we amplify and feedback the signal proportionally, but we also derive it and amplify it and feed it back in its derived form. In this case, we call the position error gain Kp and the velocity error gain Kd. One side note at this point, which we will not go into further in the next steps. In the case of the velocity control, we speak of a PI controller because we amplify and feedback the signal proportionally and also in its integrated form. In both controllers, the position error and the velocity error are multiplied by a constant and the results are added. The difference between PD position control and PI velocity control is therefore basically only the different purpose. The question now is how to program something like this. For this consideration, we assume that it is a single-axis control and that the robot is a simple mass. First, we define meaningful names. Then we describe the signal flow as a formula with a simple solution: force equal Kp multiplied by position error plus Kd multiplied by speed error. We can now see that the whole PD control is actually just one simple program line. If we want to program this on a microprocessor, we have to add a few lines. Calculation of the position error, which is equal to the set point position minus the actual position. Calculation of the speed error by numerical derivation. Calculation of the control algorithm itself. Save the old values that we need for the numerical differentiation for the determination of the speed error. Very often the green colored part in the program is provided as software component PD controller. This allows us to view the PD controller's finished block, which makes our representation a bit clearer. So we can represent our system with only two blocks. On the left the PD controller and on the right the controlled system, that is the dynamic behavior of the mass. Perhaps we should also model the controlled system a little bit more precise. Basically, for a simple mass, Newton's law simply applies. The force is the mass multiplied by the acceleration, so the acceleration is the force divided by the mass. The velocity is determined by integration and the position by further integration. We have found the model of the controlled system for a moving mass, shown here in purple. The system corresponds to a controlled servo-axis. If, for example, it is only a simple motor, we use the moment as a force and the motor inertia as the mass. Many of you who already know control technology will have missed the integration control and will argue that the PID controller is much better than the PD controller because it reduces the control error to zero at standstill, even when there is a command friction. Basically, this is not completely wrong, but the integrator has the big disadvantage that it interferes with my model-based control, often negatively affect the system dynamically, corrects control errors only with a long delay, and its behavior hides the physical effects of the model and makes their interpretation practically impossible. In principle, the eye controller is the sledgehammer method to get rid of remaining errors without knowing more about them and without having to care about the cause. For the design of model-based control systems, however, I prefer to see control errors, to recognize error sources in the model and to compensate them directly in the model. This is the reason why we add the eye controller only at the very end when the control runs almost perfectly to compensate for remaining errors. As a next step, watch the video about the physical meaning of the robot control parameters. All course materials are available on Moodle at online.robotics.ch. For the implementation, we recommend the open source robotic framework EROS, which we also use in this course. You find it on eros.org or wiki.eros.org. We are happy to answer your questions or suggestions in the forum on Moodle, or if you are not enrolled in the course, in the comments here.